So good day. So next mechanism is age or precipitation hardening. So there's a good story behind this discovery of age or precipitation hardening, and this mechanism, this precipitation hardening mechanism is developed by Alfred Williams. Okay, and his discovery is based on this martensite formation. Martensite formation. How this martensite is formed? We have austenite. After heating, the material sample is in austenite state. Then we suddenly quench the austenite steel to produce martensite. This is the austenite transformation. Martensite transformation. Okay, so we need high rate of cooling for austenite production. For example, we heat the material in austenite state, then we dip that material in the water. Okay, so we got very high cooling rate. We can produce martensite. So the resulting solid is martensite. Okay, and what are the properties of martensite? Can you give any one property of martensite? Ityas?
Brittle.
Is brittle.
Brittle.
Brittle. Then
Hard. High strength.
very high hardness.
Hard.
Yes, yes. Very hard. Hard steel is called. This is the maximum hardness we can achieve in a steel. That is martensite structure. Martensite structure is produced by quenching. High rate of cooling from austenite state. High rate of cooling. Okay. So the Alfred Williams, he discovered this age or precipitation hardening, and he did some experiment based on this. So for steel, by very high cooling rate or quenching, we can produce very hard material which is called martensite. Then where can we apply the same principle for aluminum? Because aluminum is an important engineering material. How can we make very hard aluminum material? We can do same operation of steel. How this steel, martensite steel is produced by quenching. So this Alfred Williams conduct an experiment similar to this martensite formation on aluminum. Okay, so he prepare a sample. Then this Alfred Williams heat this sample into a particular high range temperature. Then similar to martensite formation, after heating, we maintain the sample at that temperature for some time. That is called holding. We hold the material at that temperature for some time. Then so this is holding, this is heating, this is temperature, this is time. Okay. Then he rapidly quenches the material to room temperature. So this is very rapid cooling or quenching. Okay, so he quenches the material, aluminum material. Of course, for steel, after quenching we got martensite, which is very hard. But unfortunately, after quenching aluminum, he got a material or microstructure which is softer than that of original material. Okay, so finally we got, after quenching, he got a material or microstructure, but that material is softer than that of the initial material. So there is no hardened material is formed. At the same time, a softer material is produced. Reverse process is occurred here. So here he totally disappointed. Okay, and he done the experiment with another temperature. He changed the temperature, this heating temperature. Again he used, so this is T1. He conduct the same experiment with another temperature T2. He hold there, again quench. Okay, again quench. But in the interesting story, after conducting this experiment, അദ്ദേഹം ഈ ഫൈനൽ പ്രോഡക്റ്റ് ടെസ്റ്റ് ചെയ്തില്ല. അദ്ദേഹം എന്തിനു പോയി? വീക്കെൻഡ് സെലിബ്രേറ്റ് ചെയ്യാൻ പോയി. ഓക്കെ, അപ്പൊ ഇവിടെ ഇത് ഇമ്മീഡിയറ്റ്ലി ആഫ്റ്റർ quenching he tests the product, but here after conducting this experiment he did not quench the test the product or hardness measure ചെയ്തില്ല. He gone for a celebrating the weekend. Then after 2 or 3 days he came back and then he test the specimen. And he found that the hardness is improved. Okay, that means this diagram, this is time. So after quenching, he maintained for that temperature, room temperature, for a long time, and at this point he got a very hard material. Okay, so this is an excellent invention. Accidentally he invented this type of increasing hardness, and this is called age hardening. After quenching, he maintained that sample at the room temperature for a long time, and that is called aging. By aging, the hardness is increased. Here the hardness is low. At this point, after quenching, the hardness is low, but after aging, the hardness is improved. Okay, so he patented that innovation, and this is called age hardening. So this is the accidental development of microstructure that is called age hardening or precipitation hardening. Okay, so this is, and then he conducted several experiments based on this, and he concluded that for aluminum, this is the variation in hardness with respect to time. Okay, this is the hardness. This is with respect to time. That means the hardness is increased with respect to aging. This time, with respect to increasing this time, the hardness is increased. At a point, this is called peak point of hardness. Up to this point, with respect to age, hardness is increased. So this is the aging point, aging line. After this is called overaging range. What happened during overaging? That means if we maintain the sample again for a long time, then the hardness is decreased. Very interesting phenomenon, right? ഒരു particular amount of time where the hardness is increased, but after that peak point, then hardness is decreased with respect to time. So this is called overaging. So when the time crosses peak hardness point, then hardness decrease. So this is the experimental investigation of Alfred Williams. So this is called age hardening or precipitation hardening. Okay, so during precipitation hardening, what happened during this aging period? What is the change in the microstructure during the aging period? Okay, he conducted the experiment, but he cannot explain the reason for this aging, the increasing hardness during aging period. But later he discovered how this is called aging and overaging period. This is the peak point. Okay, later the reason is discovered. The reason is that, for example, this is the aluminum copper alloy. Okay, so in this aluminum copper alloy, this is the liquid region, this is the solid plus liquid region, this is a single solution solid region. Okay, so I am drawing a line. So this is the point, and I'm drawing a line here. So this is the heating, quenching. This is the quenching process. Okay. Initially, I heat the material to this alpha range, to this point. in case of steel, we heat the material to Austen range, but here there is only single solid above this alpha plus liquid, and this is liquid region. So here we have only single solid solution region. This is alpha. So we heat to alpha region, that is this heating point, and then we maintain at that temperature. For example, this this temperature, 570 degrees Celsius. We maintain for a particular time, that is called holding time. Then we suddenly quench the material to room temperature or to lower temperature. Suddenly quench. So what happened during quenching? We can see when the line crossed this solvus line, this is called solvus line, the alpha changes to alpha plus theta. Alpha plus theta. Okay, alpha changes to alpha plus theta. So during quenching process, what happened is that the small particles of at this point after quenching, at this point, a small particles of theta is precipitate in the alpha matrix. Okay. So actually, this process is quenching slow cooling slow cooling line cross alpha plus theta. But slow cooling and the problem is theta size, theta phase in the size will be very big. Okay, so small cooling cooling rate this will be the matrix. Here we have alpha. In that alpha, we have coarse grain of theta. We will get coarse grain of theta. If it is a slow cooling, but if it is a rapid cooling and then aging, then what happened during aging process and rapid cooling and aging? Small particles of theta will be produced. Fine particles of theta will be produced. Of course, by the increasing the particles number or decreasing the size of these particles, grain boundaries or phase boundary will increase, and as well as the dislocation is the more chance for the dislocation motion precision. Okay, so by this rapid cooling and aging, a small particles of this theta phase is formed on the alpha phase. So that this theta particles is called precipitate. So by this theta precipitate, the material is hardened. Okay, so that is the reason for age hardening. So during the strength and hardness of some metal alloys may be enhanced by the formation of extremely small uniformly displaced particles of second phase. Theta is the second phase in that case of aluminum copper alloy. Okay, so extreme and uniformly displaced particles of second phase within the original phase matrix. Here alpha phase matrix. This must be accompanied by the phase transformation that is induced appropriate heat treatment. We can use appropriate heat treatment. Here in this we have used this heat treatment. Heating, holding, quenching, then aging. The process is called precipitate hardening because all the small particles of new phase are precipitates. This is called precipitates, and which is age hardening is also used to designate this procedure because the strength develops with respect to time. Okay, as the alloy ages. So precipitation hardening is accompanied by two different heat treatments. The first is the solution is heat treated, in which the solute atoms are dissolved to form single phase solid solution. We already discussed the alpha phase is formed initially. Alpha phase is formed initially by heating. Then after that, the second is the precipitation heat treatment. Okay, where quenching is started, then we maintain the quenched product for a time. It may be at a room temperature or maybe at a high temperature. It's like a tempering. Okay, so but after quenching only, after this this aging time only, we get a hardened material. But in case of steel, we got at this point also we got a hard material, martensite. But in case of aluminum-like material, we got only hard material at this point after this aging. Okay. So finally displaced particles of theta or any other second phase particles are formed, and during the aging period, that is called age hardening. That is the last one. So this is the figure showing the age hardening of the aluminum alloy. Okay, any doubt? Any doubt regarding age hardening? So with the time only, after Konji, we have to maintain the sample for a particular time for proper diffusion, and this during that time actually the second phase particles is second phase particles is displaced in the matrix of the first phase during the aging period. Okay, any doubt? Age or precipitation hardening? So the last one is displaced hardening. Similar to this precipitation hardening, in displaced hardening, fine particles of one phase are added to the another phase which is weaker. Okay, so we have a weaker phase. In the weaker phase, we add fine particles of one phase. It's almost similar to the precipitation hardening. So fine particles are added in a minor quantity. Fine particles act as obstructions for the dislocation motion. This will increase the material strength. Okay, so this is not commonly used dispersion hardening. The precipitation hardening is very important. We use this precipitation hardening in different materials to improve the strength and as well as hardness. Okay, so these are the 5 types of strengthening mechanisms. Okay, any doubt in this? Just to go through this. It's very important. The strengthening mechanism is very important. It may ask us an essay. So study this 5 strengthening mechanism. In this 5 strengthening mechanism, the strain hardening or work hardening is an important one, because in your syllabus, this strain hardening or work hardening or cold working is a separate heading. So study this work hardening or strain hardening deeply and study these 5 strengthening mechanisms. Okay. Next class, we will study about the what are the effects of different alloy elements. Okay, effects of different alloy elements. Any doubt?